Hi everyone, I'm Leo Tscata from University of Nevada, Las Vegas. I'd like to welcome you to the last series of webinars summarizing the latest release of Gravitational Wave Transient Catalog, GWTC 5.0. Today, we are going to be hearing about tests of general relativity and detailed property of released data. In terms of the format, we are going to have two presentations about each of the topics, and then move on to the panel discussion, taking questions from audience. So if you have a question during the talk, please don't hesitate to type that into Q&A section or verbally ask during the panel later. So without further ado, I would like to pass this to Elisa, who is going to start off that presentation.
Yes, thank you. Hi everyone. I am Elisa Maggio, a researcher at INFN in Rome, in Italy, and I'm happy to share with you the latest results for test of general relativity with the gravitational wave data from the fifth gravitational wave transient catalog. So here you can see the link of the paper in the archive, which was released yesterday, as well as the links for the data release and the public paper. So here today, we will be presenting the results of the paper. I will give an introduction and an overview of the paper. Elise Sanger will discuss parameterized in-spiral tests of general relativity, and Nicole Cusid will describe ring-down test of general relativity. Then we will have a panel discussion answering to your questions, and also Shobit Ranjan will answer to your questions about the residual analysis, as well as Johannes Noller about a polarization test, and Apratim Ganguly. So going into the overview of the paper, well, up until now, we have seen that gravitational waves are a good probe for testing gravity in the strong field regime and in the highly dynamical one. So far, we have observed many gravitational waves emitted by the coalescence of compact objects, such as black holes and neutron stars. And here you can see how the gravitational waveform looks like during the coalescence of compact objects. So we do have an in-spiral stage in which the two objects orbit around each other, followed by a plunge merger stage where the two objects coalesce. And finally, there's a ring-down stage in which the final remnant settles down to an equilibrium configuration. In our test of general relativity, we test the consistency of each stage of the waveform with the predictions of general relativity. And in this latest paper, we present the results of 7 tests of general relativity applied to our data. And here in this table, you can see the main quantities that are constrained, as well as the improvement with respect to previous analysis. Now, during this presentation, we will go through each of these results more in detail. To start with, we select the events from the fifth gravitational wave transient catalog, which is the data until the second half of the fourth observing run of the LIGO-Virgo-Cagra detectors. And in particular, we select the events that are observed by at least 2 detectors and have false alarm rates smaller than 10 to the minus 3 per year. Here in this paper, we present the testing general relativity results for 77 new events. This brings the total number of events analyzed in the cumulative catalogs to 168. Now, 72 of these new events come from the second part of the fourth observing run, whereas 5 of these events are coming from the first part of the fourth observing run, due to their increased significance in updated search results. We combine the analysis of these new events together with the previously analyzed ones to provide strong constraints on general relativity. In doing our analysis, we apply Bayesian inference techniques to estimate the parameters that can possibly deviate from waveforms in general relativity. After analyzing the selected events, we combine them in two possible ways. We apply a restricted approach, which assumes that the deviation parameter is common across all the events, and the joint constraints are obtained by multiplying the posteriors from individual observations. We also apply a hierarchical method, which assumes that the deviation can vary across the different observations. And in this case, the distribution of the deviation parameters is modeled using a Gaussian population. Now, going into the results of the analysis, we first present the residual test. So, as you can see in the plot here, this analysis subtract the best fit general relativity template from the data and checks whether there is any excess power in the residuals. From the analysis of the latest catalog, you can see that for all the events, the residual are consistent with detector noise. Here we are showing in blue the measurements coming from the latest gravitational wave transient catalog, and in gray the hypothesis that the measurement is described by detector noise. So the fact that the blue area is inside the gray area means consistency with noise in terms of residuals. We also test for additional polarizations than the ones predicted by general relativity. So in this case, we perform a polarization test by constructing the null stream, so a linear combination of the data, which allow us to constrain possible non-tensorial polarizations on top of the two tensorial polarizations predicted by general relativity. Now, in this plot, we can see the log base factor, which tell us the evidence for additional polarizations on top of the GR1s. And when these values are negative, it means that the general relativity hypothesis is favored. So from this analysis, we didn't find a strong evidence for additional polarizations beyond the ones of general relativity. And also the log base factors improved with respect to the previous catalog. And here we report the numbers in which a negative number means disfavoring general relativity hypothesis, and the positive number means favoring general relativity. Now, with this, I will hand it to Elise.
Hello, I'm Elise Sanger. I'm a PhD student at the Max Planck Institute for Gravitational Physics in Potsdam, and I will tell you a bit more about the parameterized inspiral tests performed as part of the testing GR catalog. So for parameterized inspiral tests, they test the binary dynamics and the gravitational wave generation during the inspiral phase. So this can be modeled in GR using post-Newtonian theory, where the dynamics are expanded in the velocity of the binary, phi here in the equation. And here we show the phase as a function of frequency. And in this equation, you see two coefficients that are highlighted in blue. These are the Pn coefficients that GR predicts their value of, depending on the mass and spins of the black holes. And in beyond GR theories, these coefficients can be different. So to test for these, we add a generic deviation delta phi in the non-spinning part of the coefficients, as shown in the second equation. On top of doing this for the coefficients that are there in GR, we also add a -1 PN coefficient, which is corresponding to dipole radiation, which does not exist in GR, but can exist in beyond GR theories. And we add a 0.5 PN coefficient, which also vanishes in GR. So we add these corrections during the inspire regime and switch them off towards the merging and ring down so that the merging and ring down looks the same as for a GR waveform. And when performing these tests, we always vary 1 PM parameter at a time. It is possible to vary multiple parameters at a time, but you will get less constraining results, and varying 1 parameter is sufficient as a null test. Next slide, please. So we use two different pipelines that perform this test. The first one is the flexible theory independent method. This uses the SUBNR V5HM ROM waveform model, which is a non-processing effective one-body waveform. And the cutoff between of the corrections at the end of the inspire happens at the peak frequency of the 2-2 mode. The second pipeline we use is a test infrastructure for general relativity, short TIGR. It uses the IMAR Phenom XPHM waveform model, which is a processing waveform model, and the inspire ends a bit earlier than the FTI, namely close to the frequency at the minimum energy circular orbit. Next slide, please. So performing these two tests, we find a consistency with GR for all the events analyzed. We also combine the results for the whole catalog in two ways. We use the restricted approach, which is shown as a solid line in the figure, and we use the hierarchical approach, which shows as the field violence in the figure. On the left in red and orange is FTI, and on the right in black and blue is TIGR. GR in this figure would correspond to a value of 0, which indicated by the gray line, and we see that all these posteriors are nicely consistent with GR. You see that at high PN order, FTI gives a bit tighter bounds than TIGR does. This is because of it probing more of the latent spiral. Next slide, please. So we have these nice posteriors on the deviation parameters that we can also turn into upper limits on the magnitude of the deviation. So here we show the results for FTI once again in red and for TIGR in blue. The filled diamond and the filled square are the new results from the latest catalog, while the unfilled diamond and the unfilled square are the previous catalog. So see that all the results improve, they become a bit tighter, the upper limits, and we get improvements that are between a factor of 1.2 and 2.6, depending a bit on the PN order. And the individual event results are shown as the horizontal lines, and we highlighted the best event at each PN order. We also have at -1 PN the results from the binary neutron star GW 170817, which are the best constraints still at for dipole radiation. And are about an order of magnitude better than the previous bounds. So next, I will hand over to Nicole for the ring down.
Hi, everyone. My name is Nicole Husid. I'm a PhD student at Stony Brook University in New York, and I'll tell you about the ring down test that we performed as part of this latest catalog. So when two black holes merge together, they produce a remnant black hole that emits gravitational waves as it settles down to some stable solution at late times. And this corresponds to the ring down phase of the overall gravitational waveforms. And this emission looks like a collection of modes called quasi-normal modes or QNMs. These things look like exponentially damped sinusoids with some frequency f and damping time tau. And so below you can see an expression for at sufficiently late times after the merger of the two black holes, what this gravitational wave emission looks like in the ring down. And so it's a sum of these QNMs where each of them is given an index label of LMN, where L and M indicate the angular structure of the QNM. And n equals 0 indicates a fundamental mode, and any n greater than 0 indicates a higher tone or more highly damped tone corresponding to that fundamental mode. And so this collection of Fs and taus, or frequencies and damping times for all of the QNMs, makes up the spectrum of QNMs for a black hole. And in GR by the no-hair theorem, this tells us that the QNM spectrum is completely determined by the values of the final mass and spin for the black hole. And so on the next slide, I'll explain how, leveraging this theory, we use 3 different pipelines to perform ring down tests with these things in mind. So first is the ring down pipeline, which operates in the time domain by resolving different QNM frequencies or different modes in only post-merger data using templates comprised of only QNMs. And so this permits independent measurements of the properties of the remnant black hole. And additionally, if we can resolve multiple modes in the post-merger data, then we can apply additional freedoms to the frequencies and damping rates of the subdominant mode that's detected in order to constrain deviations of these things from the Kerr prediction. Which is a means of testing a GR. And next, the quasi-normal mode rational filter, QNMRF, is also a time domain analysis, but it applies filters in the frequency domain to identify subdominant modes that yield remnant mass and spin property measurements that agree with those of a full signal analysis. And then finally, PSEOB&R V5PHM is a frequency domain analysis that leverages the entire waveform, not just post-merger data, and it introduces fractional deviations to just the fundamental QNMs, so the frequencies and damping times, in an underlying GR model of the entire waveform. So on the next slide, I'll get into the results. So first, we can assess the consistency of the measured remnant black hole properties that we get from just QNM only analyses using the ring down pipeline with those that we get from the full IMR analysis. So what we do is, for the handful of events shown here, we analyze the post-merger data across a range of start times ranging from blue at the earliest to red at the latest with respect to the inferred peak time of the signal. And we analyze these with a single damped sinusoid, or just a single QNM that we expect to be consistent with the dominant L equals M equals 2 fundamental mode. And so you can see that the empty contours corresponding to the results of the QNM only analyses in later times in red overlap with and agree with the filled red contour, which corresponds to the measured remnant properties that we get from a full signal analysis. And now on the next slide, for a particular one of these events, GW240621, multiple pipelines, namely ring down and QNMRF, find evidence for additional mode content in the post-merger data, specifically the first overtone of the fundamental mode, the dominant 220 mode. So first, on the right-hand side, we see this evidence in the top panel of the results from QNMRF, which shows a greater than 0 detection statistic, which supports the hypothesis for 2 modes present in the post-merger data over 1 mode present in the post-merger data. And for that same range of early times in the bottom panel, this corresponds to a quantile on the y-axis, which has a lower value, which indicates a better match between the remnant black hole properties inferred by both the QNMRF pipeline and the full signal analysis. And on the left-hand side, if we use the ring down pipeline to analyze the post-merger data with 2 modes in our QNM template, so the fundamental 220 and its first overtone, the 221, I'll draw your attention to the yellow markers, which at early times show that the amplitudes of those 2 modes included in the template are inferred at the 90% credible interval to be non-zero, and also decay self-consistently over time across the different analysis start times, and in agreement with this gray exponential decay, which is the trend that we expect for free-ringing damped sinusoids. Now, there is also some evidence for additional high-frequency content in the post-merger data for this event. And this could be consistent with non-Gaussian noise or an artifact of that sort. But because we can't unambiguously characterize that high frequency content, we then cannot use this event to constrain deviations from GR spectroscopically by applying deviations to the subdominant overtones, frequencies, and damping rates. And finally, on the last slide, we look at the results of constraints of parameterized deviations to a GR waveform with PSEO BNR. So at the bottom left, you can see how these fractional deviations are implemented into the model, such that GR is consistent with delta F equals delta tau equals 0, which is at the crosshatches in the plot above. And you can see the posteriors on these two deviation parameters for all of the events that have been analyzed, as well as the posteriors for the combination of all of these events. Namely, I'd like to point out that the light blue posterior corresponding to the constraint from 250114, which is the loudest event of our catalog with a signal to noise ratio of about 80, gives a tighter constraint on these deviations alone than we obtain from the hierarchical combination of all of these posteriors. And on the right-hand side in the table, I'm also showing you the GR quantiles that we get for these combined results with PSEO BNR. And the quantile just indicates how much of the probability distribution for these combined results we must consider in order to encapsulate GR, or the 0 crosshatches from the plot on the left-hand side. And you can see, so the lower the quantile, the better agreement you have with GR. And you can see these numbers have decreased between the previous catalog, GWTC4, and this newest catalog, GWTC5. And GW250114, our loud event, is largely to thank for that. Though we do still notice that the null hypothesis of 0 is still in the tails of these combined distributions, and this is likely due to the limited size of our catalog. And finally, on the last slide, for both the in-spiral tests that we've done with FTI and Tiger and the ring-down test that we've done particularly with PSEO BNR, we can map some of the constraints that we've obtained to specific parameters in beyond GR theories or alternative theories of gravity. And in this table, we're providing the upper limits that we obtain on some of these beyond GR parameters from this mapping. And in the rightmost column, you can see that our upper limits agree with the existing constraints that we have from other works. And with that, we conclude.
Thank you, folks, for the TGR presentation. So I think we can move on to the presentation on open data properties.
Yeah.
Yes.
So hi everyone. For this presentation, I will try to get into open data for like in the LIGO-Virgo context through the O4B run. For this presentation, I'll be presenting. My name is Pierre-Alexandre Duverne. I'm currently a postdoc at Paris Cité University in Paris, France. And with me, I have two panelists, so Ken Blackburn from Caltech and Agata Trovato from the University of Trieste in Italy. So everything I will be describing is available on arXiv at this identifier. And for this presentation, I will try to give you an overview of what kind of open data science is done in the LIGO-Virgo-CAGRA collaboration context. And the general idea behind open data science is to make the data, the code, and the publication as accessible as possible to the public to ensure to have a transparent, accessible, and reproducible research. And this is done following some guiding principle that can be summarized with the acronym FAIR for findable, accessible, interpretable, and reusable. And in that domain of open data science, the LBK collaboration is highly active through a dedicated working group called Gravitational Wave Open Science Center, or GWOSC, for the rest of this presentation. The GWOSC main responsibility in the LBK collaboration is to make the data public and accessible, and this is done via the main website here, gwosc.org. And you have here a screenshot of the front page of this website where you can see that you have access to the data and also to the various resources provided by GWOSC and the LBK collaboration. Following the FAIR principles, one of the other important role of GWOSC is to make those data as accessible as possible. And this is done in different ways. First, you have some publicly accessible tutorials here on this website, where you will be able to learn how to use the tools provided by the LBK collaboration that have been developed within this collaboration and maintained by GWOSC. And also, every year, there's a workshop that's organized by the growth group that is dedicated to having newcomers and students starting working on gravitational wave astronomy. And it presents itself as a presentation by experts from various domains related to gravitational astronomy from the LBK collaboration. And then you have dedicated attend session for which different experts in data analysis can help you working with data and gravitational wave tools. And finally, one other important role for GWOSC is to make, every time there's a data release, a paper that is describing how the data is processed, accessible, and where to find them. And this is the case for this O4B data release. And you can find this paper on the archive with this identifier here. So now that I've briefly introduced the responsibility and the role of GWOSC inside the LIGO-Virgo collaboration, I'd like to get into more details about which data you can have access to with GWOSC. And the first primary data product that is provided by the group is called the calibrated strain HOT. Basically, after your instrument gets a signal output, you have a process called calibration that allows you to convert this into an actual gravitational strain, which is a measurement of the deformation of the space-time metric. And this is what you want to analyze to find new gravitational signals and to analyze the candidate event you have detected. This calibration process is basically trying to estimate how the mirror motions and the control signals influence the interferometer output so that you can compare that into the actual HOT strain. And in the end, you end up with an estimation of the statistical uncertainties and the systematic errors of your interferometer. And this is what's highlighted here on the right-hand side plot, where you have these uncertainties summarized for the phase and magnitude domains. And this figure can be found in the open data paper of 4B. And after this calibration process has happened, you obtain the HOT time series, which is what's actually used for making actual gravitational wave astronomy, so Trojan searches, or estimation of parameter, for example, once you have detected a credible candidate. On the right-hand side here, you have an example of an HOT data segments that contains the first detection of a gravitational wave in 2015. What I've described in the previous slide is a strain data that's provided by default, and that's user-friendly and clean, and that you can use as it's provided by GWOSC if you want to make your own analysis or if you want to test some algorithm, for example. But in order to be as exhaustive as possible, the GWOSC group also released what's called alternate strains, which consist of strain data, but without some of the post-processing processes that has happened after calibration. Some of them are made for removing narrow or broadband noises, and others are made, for example, for removing loud transient nodes that are called glitches inside LIGO and Virgo collaboration, and that could hinder the analysis. So either on the detection side or on the analysis, for example, if you have a look glitches on top of a gravitational wave signals, it prevents you from properly estimating the parameter, for example. And these kind of intermediate data products are provided by LIGO and Virgo through GWOSC. Another important tool that's provided by the group is called Timeline. It provides you, for example, the segment lists for when the data are available or not, because during an observing run of the LIGO and Virgo collaboration, the detector is not always recording data for various reasons. And this timeline tool provides you with the segments of time where you can retrieve data from a given interferometer. The timeline tool also provides you with the data quality category, because for some reason you may have some data quality issue inside your data, and Timeline provides you the data segments when some data are not completely trustable, but I will get back to that in the next slide. Timelines also register the hardware injections. So these kind of injections are made in order to test whether your algorithm, detection algorithm are working properly by actually acting on the mirror to simulate gravitational wave signals. And then it allows to check whether you properly detect your gravitational wave signals when they are injected. On the bottom of this slide, you have an example plot for all the segments for which data are available during O4B for the three instruments that participated to the run. So LIGO Hanford, LIGO Livingstone, and Virgo at the bottom of the plot. Another type of data you'll be able to find in WOSC are called the auxiliary channel. Basically, each interferometer records a lot of different channels, so about 200,000 per interferometer, which consists of data acquired by different instruments, being seismometer, accelerometer, magnetic probes, etc. All of these allows to probe all the environments that's influencing the instrument and or the instrument behaves in that environment. And among these 200,000 channels, about 25 are used by H1 and L1 for making assessment on some potential data quality issue. And these channels have been selected because they are good proxies for estimating whether or not you have the data quality issue in your H of T strain data. And then based on those auxiliary channels, we can create flags to veto these data. And these flags are spread into three categories, which indicate the kind of issue you're facing. If you have a Cat1 issue, it means that you have a technical problem or a critical issue that involves a key detector component that's not operating in a nominal configuration. Cat2 flags marks time where you have a noise coupling between the strain channel and one of the auxiliary channel. And this might be, for example, due to a high ground motion or some environmental disturbances. And the Cat3 flags time with statistical correlation between the strain and the auxiliary channel where the coupling is not completely understood. So to summarize a bit what I've described in the previous slide, all these data are accessible on the main page of the website. If you click on the Get Data button and then on the Datasets one, and you can see here that for the O4B data release, you can find all the data I've mentioned. So the 4 kilohertz and 16 kilohertz data corresponds to different sampling of the user-friendly and default H of T calibrated strain that you want to use for any analysis you want to perform for detecting gravitational wave or estimating parameter, for example, on a candidate event. Then here you have the timeline tool for which we'll find again all the segments and averagation, for example. Here you have the auxiliary data if you want to work with that. The alternate strain if you need to work with some intermediate data products for H of T. And also the documentation that describes in great details all of these data, how they have been processed and how to use them. Also, on the GWOSC website, you can find what's called the event portal, because GWOSC also provides access to all the gravitational events that have been identified and published in the various gravitational wave transient catalogs, or GWTC. And this event portal gives you access to all the analysis products that are included in those catalogs, being parameter estimation posterior, data segments containing signals, spectrogram, etc. And you can have access to that event portal by clicking on the Get Data button and then Events in Catalog that should send you on the event portal main page, where you'll be able to find the latest GWTC Transient Catalog data release, the previous releases here, the page with all the individual events that have been identified in the various runs and various data release. And here you have a query form where you can select a subpopulation of events that you that you're interested in if you want to work on those subpopulation. And if you go on the event portal, you have to understand that each catalog is cumulative and contains all the previous events with updated information when necessary, because it may happen that during a data release, some previously already analyzed data are reanalyzed and some information appeared or some analysis is improved, and then you have different information compared to the previous data release. And all of this is documented and described on the event portal. And then if you want to check a specific event, you can click and you should arrive on the similar page where you have a lot of information about each individual event. So the metadata about the events, such as the GPS time when it's been detected, its name, and its identifier in the database. For example, you can also see the GCN message that's been sent and distributed once it's been detected online. But you also have access to all kind of different search results provided by the search pipeline. Here you have, for example, CWB, which is working for burst-like triggers, GSTLILE, which aims at finding compacted Bernoulli coalescence. You also have spectrograms and PE results if you want to work on estimation of parameters. And all of that is, you can gather that on the event portal on the individual event page. And you can see here that you have also, you see the spectrograms and the interactive plotting tools. In addition, it may happen that some events are individually interesting for some reason. And in that case, you have different papers published by the LBK collaboration for this specific event. And this is, for example, the case on the right-hand side example, which corresponds to a binary black hole merger that was extremely loud and detected during O4B, and it triggered a publication by LBK. And you can find this paper on the event page on the top left link here. A quick word also on the fact that you can access to these GWOS data not only via the main website, but also in a more automated way using Python, as GWOS data can be accessed with a library called GWPy that you can find here on GitHub. And with this library, you should be able to access to all individual events, as I've presented in the previous slide. So you have peer results, spectrograms, metadata, etc. You also have access to the calibrated strain H of T, the alternate frames if you need to work with some of these intermediate data products, and the auxiliary data if you need them. It should be fairly easy to use, as you can see here on the right-hand side screenshot, where you have a bunch of Python line that will work around a specific event that's given here with its database identifier, and then you can fetch some event time for each event parameters, strain, and data quality issue to basically everything I've described in the previous slides. So the short conclusion here is the group that's responsible for the open science in the LBK collaboration. It provides a wide variety of data and data products that are central for obviously gravitational astronomy, but not only, especially in the context of multi-messenger astronomy. Having access to well-documented and exhaustive data from gravitational observatories is crucial, for example, when you're trying to find some coincidences with neutrino observatory or gamma ray observatory, and having that is a huge advantage. Also, I'd like to insist on the fact that every year GWOSC organizes a workshop to make those data more accessible and to allow students and newcomers to manipulate them and to get familiar with gravitational astronomy. So feel free to attend it if you want. The next session should be in April 2027. And in the meantime, you can also have a look to the tutorials if you want to get familiar with this data and try to work with gravitational wave astronomy. And if you have questions, you can also reach out to the GWOSC group directly on ask.eguin.org, where you will be able to get in touch with GWOSC people and have your question answered. So that's all for me. I'd be happy to take questions.
Thank you, Pierre, for the thorough presentation or overview of the open data. And so from here, we can move on to the panel session. And we have already got the question which was answered by Nicole about the sudden rise in amplitude at the time of T minus T peak 18. Nico, did you have anything to add to that? Otherwise, we can move on to the next question, though.
Yeah, just to reiterate, you see it because the median shifts, it looks like a rise in the amplitudes, but it's really just the posterior is broadening at that time, which we do expect to happen as the SNR continues to decay.
All right, thank you. So we have another question from Huri, which seems to be about the polarization kind of contents or composition. Johannes, Did you want to take this?
Yeah, I was about to type an answer, but maybe it's easier to just answer live. So we have not explicitly. So explicitly, what we've just done is adding a scalar or vector polarizations to our standard tensorial degree of freedom as you have in general relativity. It's quite easily possible, right? So we could, for example, your questions about Vierbein style mechanisms. So you can decompose and understand, I guess, how those map to helicity and polarization modes as well. And so there's basically a mapping between alternative theories to different polarization modes in sort of somewhat analogous way to something we do in the paper in other contexts. I think you saw, for example, in the very final slide of our presentation, this mapping from parameterized constraints to more specific models. So we could do something similar in this context as well. But we have not specifically looked at Vierbein constraints for that.
Thank you. Phil, did you have any follow-up on this? Okay, he seems happy, so we're good. So I wonder if there's any other questions or any other follow-up from TGL folks. Otherwise, I actually had one kind of naive question that I hope that might trigger some discussion, which was about like event selection for TGL test, which is I think conventionally said to be one per far less than one per thousand years. And I have people looked at like relaxing the condition and to get more events for better statistics, or would that just bring another noise contamination?
Yeah, relaxing that criteria may lead to more contamination. Also, each testing GR analysis has then additional criteria to better constrain the parameters they are looking at, based, for example, on the signal to noise ratio in the in spiral or in the post-merger part of the signal. And the events at the threshold of these criteria may contribute to some systematics with respect to the ones that are the clearest ones observed until now. So expanding current criteria may lead to some features that need to be well understood. And also, we do have the two detectors criteria, which allow us to be safer concerning than detector noise. And we have seen in the past that for a particular event, GW230814, applying test of general relativity there, which was observed by only one detector, may lead to some inconsistencies. So these are the reasons that are leading us to this choice of the selection. But yeah, of course, one can look into also relaxing them.
That makes sense. Thank you. Agatha has her hand up, so please go.
Yes, hi. Just a curiosity, since you have talked about this. So Elisa was just saying that you need the two detectors. Is it fine if one of the two is Virgo, which is less sensitive, or it's a problem in your case?
Oh, indeed, here we do have in this catalog many events observed by Virgo and one LIGO detector between Livingston and Hanford. So even if the sensitivity of Virgo is not the same as the other LIGO detector, this contributes to the testing general relativity analysis. So it's good to have also information from Virgo. And I guess that for polarizations, then having 3 or even more detectors then is even better than.
We would love to have 10 if possible, but for now 3 will have to do.
So yeah, I was going to ask about what benefit we can get for expanded networks. So would that polarization, content test would be the major one in the case of like expanded network?
I mean, I think it's far from the only one, but maybe I can at least say an entry word for polarization. So for at least I mentioned this concept of null streams, right? So if you have n detectors, you can basically combine n minus 1 so-called null streams, right? Where you basically find some extra polarization you're looking for. You're basically saying, well, we're going to isolate that would-be polarization. And so then we can look at it, right? So if it's not there, so if it's just vanilla GR with tensorial polarizations, then you just find consistency with 0, and that's good, right? If you have some confirmation there. But if you see something there, then you found something interesting, some deviation from GR with some given significance. So having more detectors buys us 2 things. One, it buys us having more of these combinations, right? So we can look at more complicated polarization patterns. And secondly, even for a single polarization, we can include more complicated effects. For example, at the moment, we are not fully including precession, some underlying physical effects like this there. So if you want to model more complex waveforms, taking that into account, that's also something where it helps if you can build up more complicated null streams with more individual ingredients. So for sure, for polarization, it would help a lot to have a larger detector network.
Right. That sounds reasonable. So Elisa has a hand up first. So do you want to add with that?
Yes, I wanted to add to that I mean, besides for certain tests where having more detectors is very nice for like in the polarizations where you actually needed to construct your null stream. It especially going from 2 to 3 detectors, the improved sky localization can help a lot in breaking degeneracies, because adding these extra parameters sometimes introduce new degeneracies that you otherwise might not really have any problems with in GR. And besides that, there's maybe the slightly more obvious that having more detectors makes it less likely that you have some correlated noise influencing your test. And you have increased signal to noise ratio, which could also improve the tests.
Yeah, that makes sense. The Nicole?
Yeah, honestly, echoing a lot of what Elisa just said. So in terms of the sky localization, particularly for the ring down and the QNMRF analyses, to configure our analyses, we rely on PE from the IMR analyses, including establishing or fixing sky location and the inferred peak time of the signal and whatnot, and having more detectors to have a more precise sky location. The sky localization obviously helps with that, and is a better informant for the configuration of our analyses. And in terms of the SNR boost, in cases like what we just saw with GW 240621, for example, where there's some additional content that we're trying to investigate and learn more about and characterize better. It's often helpful to do things like analyzing the data just from one detector at a time. Obviously, when you do that, you lose a lot of SNR, especially for a post-merger only analysis where you're already cutting the SNR of the data you're working with like at least in half. So the more detectors you have that you can include in your coherent analysis while trying to characterize any additional content in the data, the better.
Yeah, thank you for adding that. Shobit, did you want to add to that?
Yes, going based off of everyone else's points about a bigger detector network, The whole point of residuals analysis is to find excess coherent power. So a more expanded network will obviously help pinpoint deviations better if there's coherence between multiple detectors. Even for the example of 230814, which had a section of residual analysis in there, it didn't basically wasn't very effective at doing that because it was a single detector event. And yeah, a bigger network would definitely help with pinpointing where the deviations are coming from and if they're present at all in the noise.
Yeah, that makes sense. Thank you. Since we talk a lot about testable generativity, I kind of like shift the gear a little bit towards open data. Then I wanted to maybe ask either Ken, Agatha, or Pierre about maybe future prospect, what data release will look like, or what kind of role it will play. Because as a personally who worked on or writing the results paper, as we have even more events, now we've got like almost like 400 events, and now it'll be even more for GWTC 6. And then like how we present the results in the paper might not, might be not going to be like optimal in a conventional way. And then I think that, presenting something in the online basis might serve better. And now that's where I think GWASC might play more roles on. And I wonder what any thoughts you guys have about how we can present results in general in the future.
Yeah, that's an interesting question. We already see some aspects of the growing catalog impacting performance. And I think one of the things that Pierre pointed out was that we have this query option where you can down select out of the, I don't know, 300 or so events that we have right now to the subset that's most interesting to you as an event list. So, we're constantly going to be working to improve technology. I don't know if, I'm 70 years old, and I remember when computers filled a whole room and they were a billion times slower than my cell phone. So we're all always constantly battling against performance. And technology is there to help us achieve that. But I think another aspect of this is that the collaboration as a whole should start to think about what we want to do from the bigger point of view. Now, having said that, I think that one of the things that was pointed out by Pierre, but may not have synced in, is that we do capture the full GWTC, the cumulative catalog on GWASC of all the events, and we probably always will. It's just a matter of how to present that to the user in the most efficient way, which I believe we're working towards with the query and the performance aspects of it. There is another aspect of all of this, which is beyond the events, that if you're using the data as a power user, let's say you want to analyze all of the data and create your own catalog, we do in GWASC support through, and you can find the documentation and the procedure and policies for submitting your own personalized catalog to GWASC to contribute as long as it meets certain specifications. But this requires analyzing all the data again. And maybe you have some cute AI algorithm that you use to detect events in a way that is novel and hasn't been thought about before, and you want to publish that and then also get it contributed on GWASC. If you go to the GWASC website and go to the page, the event portal page, you will find links to how to contribute as a community. Having said that, getting to all of that data, that's a large amount of data, 6 months to a year's worth of data that you want to use. There are tools for power users to get the data, which are somewhat less obvious from the data selection page that Pierre showed. But on that page, at the top of the page, there's a link to documentation for how to establish what I will call a virtual type file system on your local institutional computer system. And basically, this is using distributed data sharing servers around the world to boost performance and make it a lot easier and faster to get large data sets. And so for people that are looking at that sort of usage model, power usage, I highly recommend looking at that page. There was a lot in your question, Leo, and there was a lot of answers there. If I'm overlooked anything or glanced over anything, let me know.
Yeah, thank you. That's really thorough and thoughtful view on that. I appreciate it. I think I just following on your idea of carrying data in a way that users want. At the moment, I think the GWASC just list up the PE, like raw PE results for every single event, but might be interesting to like tie that into or incorporate other scientific data product like astrodisks or even TGR or lensing analysis so that users can maybe query things based on what they want about like what kind of like some events that have like interesting TGR results, for example. And like that's one of the way to kind of like expand the scope, maybe too much, but like usefulness of current WASC framework, I think. But just thinking out loud. Ken?
Yeah, that brings to mind an interesting and important aspect of what's available on GWASC, and that is that a lot of these papers have intermediate data products. For example, when you look at the events and you see what their masses and spin and stuff like that, those are the credible interval results. What's the results of the posterior samples that were generated in the parameter estimation process. And so for each of the events, when you're looking at the PE results, there are links to the Zenodo intermediate data products that are produced by the collaboration to get to those results. And in addition to that, on the documentation page for any particular catalog, I'll call it a release instead of catalog, but for any particular release, in the documentation, you will find usually links to other things that have been shared by the collaboration. For example, sensitivity studies, sub-threshold events. So there are links that you can find in GWAS that go to a tremendous amount of the intermediate data products that went into getting to those numbers that you see, that the small set of numbers that you see on GWASC. Although, as Leo's pointing out, that small set of numbers is getting larger with each run.
Yeah, thank you. Maybe that's something I hadn't appreciated fully, but yeah, thank you for the information. Nicole?
Yeah, I do want to just shout out since we're here on behalf of TGR as well in terms as far as data products go. We have, both Zenodo and DCC data release that's now public. It's become public along with the paper appearing on the archive a couple days ago. But since you were asking about intermediate data products and raw posteriors and things, so at the moment for timing with the archive appearance of the paper, we do have all of the data behind the figures, at the very least, for each of the pipelines available both on Zenodo and DCC, with plenty of documentation detailing how users can access the various data products and manipulate them. And run the plotting scripts. But the plan for the future for, eventually when the paper gets accepted and published, is to have another updated Zenodo data release with all of the raw posteriors that had gone into even producing these intermediate data products and the figures in the paper. So in terms of someone having access to like more specialized posteriors for whatever their science use case is, we will have that. We already have a lot of that available, and we will have that available for something like TGR, for example.
Yeah, thank you for the reminder. That's great to know. Kent?
Yeah, I just wanted to reach out to Nicole and say we're happy to advertise that on GWASC. when you have it ready, just send me an email and I'll add it to our public documentation page so that people can find it and go to it if they're on our site looking.
Will do. Absolutely. Thank you.
Thank you.
All right. I think we've got good deal among us. So I think that's we are passing the hour, and that's a good time to wrap this up. So I think thank you everyone who contributed to the presentation and discussion, and also audience participating here and asking questions. It's been great discussion. So I'll bring this back to Casey.
Yes, thank you all panelists and presenters, and I believe we can close out the webinar.
All right, thank you everyone, and thank you for organizing this, Casey, as well.